Okay, let me start with mass and weight. During the last lecture, we have discussed the forces, and today we will go into detail with the weight of an object. The weight of an object on the Earth is the gravitational force that Earth exerts on it. So here we have a mass of an object, and then the weight of this object is given with this expression you already know. Weight is equal to m times g. M is mass of the body, and g magnitude of acceleration due to gravity, and weight is given here. So here there is important information. In reality, the value of g is not constant. It depends on altitude, okay? But usually within the questions, we take it as constant. And also in other planets, g will have an entirely different value than on the Earth. Don't forget also this information. So here, let me discuss two conditions. We have a box falling body with the mass of m, and here the same box, but now it is hanged, so hanging body. Two conditions with the same mass, and what about the weight of the body? Here, this box has free fall motion, and the weight of box is given with this expression. Weight is equal to m times g, okay? G is acceleration vector, weight is vector, and then here we have mass of the object. And here we have acceleration due to the gravity, and this is the direction of the acceleration. And only force acting on this falling body is weight, okay? Weight is acting on this body due to the gravity. And the net force acting on this object is given with weight, which is equal to m times g. And look at this one, hanging body. This is hanged, it does not move. And this is the rope. Let's consider there's a sailing here. Let me draw, and then this box is hanged. So here we have a tension force, and here we have a weight due to the gravity. Weight is given with m times g, and tension force is given with t. Both of them are vectors. And what about the net force acting on the system? Since the box is at rest, it is hanged, net force acting on the system is zero. So since the net force is zero, the acceleration of the body is also zero because net force is zero. Okay, so what we see here, this relationship is the same whether a body is falling or stationary. Here we have a falling body, here we have a stationary body, but we have same weight acting on both boxes. Do we have any question here? Then let me continue with an example. Let me magnify the question first of all. Can you see the question?
Yes.
Yes.
At 2.49 times 10 to 4 Newton Rolls-Royce Phantom traveling in the positive x direction makes an emergency stop. The x component of the net force acting on it is minus 1.83 times 10 to 4 Newton. What is its acceleration? Here, what do you see? It is not the mass, it is the weight, because Newton is the unit for the force. Then this is the weight of the Rolls-Royce Phantom, okay? And then here we have another force acting on this Rolls-Royce. So what is the acceleration? At the beginning, it was traveling in the positive x direction, and then it makes an emergency stop. So this is the question. So we have to find the acceleration. Let's have a look. So here we have weight, which is given, and the mass of this Rolls-Royce can be found by using this relation. Weight is equal to m times g. If you take m, and if you put the weight given in the question, if you put the g, 9.8 meter per square second, then you can calculate mass. Here, instead of Newton, you can write kilogram times meter per square second. And square second, meter, we cancel each other, and then this is the unit of the mass, okay? We have found the mass of the Rolls-Royce. It is around 2.5 ton, let's say, or 2,540 kilogram. What was the question? The question is, what is the acceleration? So what are the forces acting on this Rolls-Royce Phantom? Force is given minus 1.83 times 10 to 4 Newton. So net force acting on the Rolls-Royce along the x-axis is given by m times ax. So within the question, acceleration is asked. So if you take acceleration from this expression, net force acting on the Rolls-Royce along the x-axis over m. So we have already calculated m, put the m here, and the force is given in the question, minus 1.83 times 10 to 4 Newton. Again, you can convert Newton to the kilogram times meter per square second in order to better cancel the units here in the equation. So finally, we will have meter per square second. Here we have minus sign. Here we have minus sign. So the acceleration of the car is minus 7.20 meter per square second. So what is the meaning of minus sign? The negative sign means that the acceleration vector points in the negative x direction. Acceleration is a vector and it points in negative x direction. So the car is moving in positive x direction and it is slowing down. Then it means that acceleration must be opposite to the velocity, right? Initial movement of the car. So it is logic. Do you have any question here? Then let's finish this chapter with Newton's third law. So what is Newton's third law? Here we have a ball and this is body A, and if this body A exerts a force on the body B, for example, a foot kicks a ball, okay? Then this body B, the ball, necessarily exerts force on body A. Ball kicks back on foot. So this foot kicks this ball, and then this ball kicks back on foot, okay? So this is the force this A applies on the ball, which is given with this expression, Fa on B, and we have the same force which is applied by the ball on the foot with same magnitude but opposite direction. Okay, this is the Newton's third law. So the two forces have same magnitude but opposite directions. Here we have the relation. This is the Newton's third law. So if you apply a force on something, then this object will apply back force on you. This is the general definition of Newton's third law. So here we have very important caution. The two forces in action-reaction pair act on different bodies. So what is the meaning of action-reaction pair? So you apply force on the ball, and then this is action force, and this ball reacts on this foot, then this is the reaction force. Then these forces are action-reaction pair, okay? So action-reaction forces. But what do you see here? These two forces apply on different objects. For example, this force applies on the ball, but this force applies on the foot, okay? Within the questions, you must be very careful. So we stress that the two forces described in Newton's third law act on different bodies. Later on, I will give you some examples on this issue and you will better understand. And for example, let's try to find net force on this soccer ball here. What is the net force on the ball? The ball has certain weight, okay? Let me draw in this direction. and the ball has this force, okay? This force is applied on the foot, okay? So you must separate these two objects when you are dealing with Newton's third law. We stress that the two forces described in Newton's third law act on different bodies. So don't forget this one. Now let me tell you something else related to the Newton's third law. Here in this example, what we have here, we have a contact, right? So due to the contact between foot and ball, the foot applies a force on the ball and the ball applies a back force on the foot. But what about non-contact forces? For example, let's consider long-range force. We can also consider that the Newton's third law is valid here. So look at the example of Earth and Moon. So here with the red color, we show the pull of the Earth due to the gravity of the Earth. And here we have a green arrow due to the gravity of Moon. Okay, so there is no contact, let's say, between Moon and Earth, but they have mutual forces acting on each other. Okay, so now let me continue with conceptual example from the book, example 4.8, which force is greater? Okay, after your sports car breaks down, you start to push it to the nearest repair shop. While the car is starting to move, how does the force you exert on the car compare to the force the car exerts on you? How do these forces compare when you are pushing the car along at a constant speed? Here, Newton's third law gives the same result whether two bodies are at rest, moving with constant velocity, or accelerating. Okay, so if you apply F force on the car when the car is at rest, so with the same magnitude of force, car applies back to you. And if the car is moving with constant velocity or accelerating, and then you are applying another force on this car, then with the same magnitude of the applied force, the car applies a force on you. So this is the Newton's third law. Here we have important information. Let me read this part because it tries to explain the mechanism of this Newton's third law. So you may wonder how the car knows to push back on you with the same magnitude of force that you exert on it. It may have to visualize the forces you and the car exert on each other as interactions between the atoms at the surface of your hand and the atoms at the surface of the car. Let me draw here. This is very nice information. So let's consider that this is the car. So you apply a force on the car and the car applies a big force on you. So these forces are equal to each other in terms of magnitude, but they are in opposite direction. So then the question, how the car knows to push back on you with the same magnitude of force that you exert on it. So here the car is made from atoms. Okay, this is just schematic representation. So here we have many atoms, millions of atoms, and also on the surface of our hand we have many atoms. So just consider miniature spring between adjacent atoms, and a compressed spring exerts equally strong forces on both of its ends. These are the atoms on the surface of hand, and here these are the atoms on the surface of the car, let's say. Okay, so you can consider that when you touch on the car, you can consider that there are springs between the atoms, and when you apply a force in this direction, this will apply a back force with the same magnitude and opposite direction. This is explained here, just to visualize the forces. Any question here? Okay, then let me continue with another conceptual example from the book, applying Newton's third law, objects at rest. An apple sits at rest on a table in equilibrium here. If it is in equilibrium, it means that the net force acting on the apple is zero, okay? Don't forget this one, Newton's first law. What forces act on the apple? What is the reaction force to each of forces acting on the apple? What are the action-reaction pairs? Here we have 4 different conditions. This is A, B, C, D. Let's start with the A. Here we have table, and here we have an apple. Due to the gravity, there is a force, which is weight, applied by Earth on apple, okay? And there is another force. Table applies a force on the apple, okay? This is normal force, F table on apple. So the magnitude of this force, weight and normal force, are equal to each other because the apple is in equilibrium. So now let's discuss the action-reaction pair for the interaction between the apple and Earth. Here we have table. This is the weight, okay, the force due to the Earth on apple, but there is a force applied on Earth due to the apple. So here I have shown you this example. Here we have moon with some certain mass, and here we have Earth with certain mass, and there is a gravity of moon and there is a gravity of Earth. So the Earth applies a force on the moon due to the gravity, and then the moon applies a force on Earth. The same mechanism here. Apple has certain mass and Earth applies a force on apple. This is the weight of the apple. And in addition to that, apple applies a force on Earth. Okay, this is the direction of the force applied by apple on Earth. Is it clear for you? So these forces are action-reaction pair, okay? Earth applies a force on apple and apple applies a force on Earth. So action-reaction pair in magnitude, they have same forces, but they have opposite directions. So now let's have a look. The C, action-reaction pair for the interaction between the apple and table. This is the table. This is the surface of the table. And apple applies a force on table, right, due to the weight. Apple applies a force on the table, and as a reaction, table applies a force, back force on the apple. So these are action-reaction pairs, and they have same magnitude, but they have different signs, different directions. Now, let's have a look this condition, D. We take the table out, we remove the table, and then here we have apple, and there is a force acting on the apple due to the Earth, this one, weight, and apple applies a force on Earth, this condition, okay? And there is no force applied by table on the apple. So F table on apple is missing here because there is no interaction between the apple and table. For this reason, this force here in this second condition is zero. So what about these forces? The force applied by Earth on the apple and the force applied by the table on apple. these are not action-reaction pairs. Okay, here we have information. The two forces in an action-reaction pair never act on the same body. Don't forget this one. Any question here? Let me continue with the Newton's third law, objects in motion. Here we have very nice example from the book. A stonemason directs a marble block across a floor by pulling on a rope attached to the block. Here we have the picture. This is the stonemason and this is the marble block. And this stonemason directs this marble block. The block is not necessarily in equilibrium. How are the various forces related? What are the action-reaction pairs? You must be very careful here. Let me start with this one. We have rope here, we have marble here, and we have stonemason here. And you must be very careful in this type of questions if the rope has mass or not. Okay, this is very important. Now, here I will discuss two conditions. So let's discuss the action-reaction pairs. The stonemason applies a force on the rope in this direction. Okay, he pulls the rope. Just consider rope here, and then stonemason pulls this rope. So this force applied by mason on the rope, stonemason, and then this rope applies a back force on the stonemason. Okay, F rope on stonemason. This is action-reaction pair. And here the rope applies a force on this block, and this block applies a force, back force, on the rope. This is also action-reaction pair. So now let's have a look this condition. Mason applies a force on the rope, and then block applies force on the rope. These are the not action-reaction pairs because they act on the same object. So this force applied by Mason on the rope and this force applied by the block on the rope. So both forces applied on the rope. So two forces acting on the same object cannot be action-reaction pairs. I have shown you here the two forces in an action-reaction pair never act on the same body. Here, let me continue with the special case. So let's try to apply Newton's second law to the rope. Here we have rope and we have a force applied by Mason on the rope, and here we have force applied by block on the rope, and then apply Newton's second law. The net force acting on the rope, is given with force applied by Mason to the right side plus force applied by the block to the left side, right? Which is equal to m rope, mass of the rope, times acceleration of the rope. If the mass of the rope is 0, let's consider we have massless rope, then this is 0, then these two forces can be equal to each other. Or if the rope is in equilibrium, it means that the acceleration of the rope is 0, then the right side of this equation will be 0. Then again, these two forces can be equal to each other. But this is only valid for special cases, okay? If the mass of the rope is 0, or if the rope is in equilibrium, you can consider that these two forces are equal to each other. Do you have any question here? Let me continue with another conceptual example from the book 4.11, a Newton's third law paradox. So here, let me discuss the situation. If an object pulls back on you just as hard as you pull on it, how can it ever accelerate? Let's consider that this stone mason, is pulling this block and rope mass, okay? So this is the force applied by mason on the rope, okay? And then rope applies a force on the mason. So let's consider that they are equal in terms of magnitude, but why mason does not move, but block moves? This is the question. The answer is related to the friction force between mason and floor and the friction force between block and floor. So due to the surface of the shoes of the mason, there is huge friction force between the mason and floor here, and due to the surface of the block, there is a smaller friction force between block and the floor. So now let's try to find net force acting on the marble block here. Look at this one to the left side. Very easy to understand. It is necessary just to concentrate on this. I'm talking about left side. So I have separated block plus rope from the mason. So what are the forces acting on this block, marble block? Let me choose the pen. Here I have force applied by mason on the block to the right side, and there is a friction force of floor on block due to the friction between the floor and marble block. There is a weight due to the gravity, and there is a normal force, okay? So these two forces are equal to each other and cancel each other. And if this force applied by mason on the block is bigger than the friction force of floor, then this block will move in this direction, right? But in this case, there is a force applied by rope on the mason to the left side, and there is a friction force of floor on mason to the right side. So how to apply huge friction forces? It is related to the surface of the shoes, okay? If you wear special shoes, then you can produce large friction forces, and then mason will not move. Is it clear? Any question here? Then let me discuss three conditions related to the free body diagrams. So what is free body diagram? Here we have a special condition. You have an object mason, you have an object rope, you have an object marble block. In free body diagram, you have to write all forces acting on this mason separately, and you have to write all forces acting on this rope separately, and you have to write all forces acting on this marble separately. This is free body diagram. Here I will show you three important ideas and techniques to use in any problems involving Newton's law. So the first one, Newton's first and second laws apply to a specific body. If the system is in equilibrium, then you have to use this one, Newton's first law, net force acting on the system is zero. If the system is not in equilibrium, if we are talking about non-equilibrium situation, then you have to apply Newton's second law, okay? So, but we must decide at the beginning to which body you are referring. So here you have to decide at the beginning you are dealing with this object, with the mason. And here you have to decide that you are dealing with this object. You have to separate this one from the others, okay? The second one, only forces acting on the body matter. Here we are talking about the forces acting on this mason, okay? Weight, normal force, friction, and force applied by rope on the mason. You have to take forces acting on this object. For example, here we have another force applied by mason on rope. You cannot use this force for this object. This is very important. Only forces acting on the body matter. Hence, once you have chosen the body to analyze, you have to identify all the forces acting on it. And another important information here, don't confuse the forces acting on a body with the forces exerted by that body on some other body. So here, for example, again, let me clean this one. We have forces on this mason, weight, normal force, friction force, and force applied by rope on the mason. Here we have another force applied by mason on the rope. So you cannot use this force for this object because this force does not act on the mason. This force applied by mason. So you cannot use the forces applied by this object. Okay, this is explained here, and I will show you some example. So this was the second important information in free body diagrams. So here I will show you very nice example. The simple act of walking depends crucially on Newton's third law. To start moving forward, you push backward on the ground with your foot. Let me draw here. So let's consider this is leg and this is foot and this is ground. There's some certain friction. And in order to move forward, we apply force like this. This force applied by human on ground, okay? And then as a reaction, the ground applies this force applied by ground on human, okay? So this is action, reaction. So what about the movement of this body? Which forces are acting on this body? So this guy applies force in this direction. This is the force applied by human on ground, let's say. And then due to the action reaction, due to the Newton's third law, there is a force applied by ground on human. And what are other forces? We have weight due to the gravity, and we have normal force. Okay, so what about the net force acting on this guy along the y-axis? If you choose positive y is this one and minus weight, and it is 0. Net force along the y-axis is 0. What about the net force acting on this guy along the x-axis? You cannot take this force into account within this net force acting on the human because this force applied by the human on the ground. Is it clear? Any question here? Then let me go back to the transparencies. Okay, now I am repeating. To start moving forward, you push backward on the ground with your foot. So you applied a backward force. As a reaction, the ground pushes forward on your foot and hence on your body as a whole with a force of the same magnitude. the force applied by ground on you. This external force, this is the external force applied by ground on the human, provided by the ground, is what accelerates your body forward. Okay? Here we have the third point in free body diagrams. We have many important information here. I will try to tell you step by step. So free body diagrams are essential to help identify the relevant forces. A free body diagram shows the choosing body by itself. For example, you have chosen this body, marble block, or you have chosen mason. Okay, first of all, you have to choose the body free of its surroundings. So you are only considering the forces acting on this body with vectors drawn to show the magnitudes and direction of all the forces that act on the body. So be careful to include all the forces acting on the body, but this is very important. Be equally careful not to include any forces that the body exerts on any other body. In particular, the two forces in an action-reaction pair must never appear in the same free body diagram because they never act on the same body. For example, here, this is the force applied by Mason on this block and rope, and this is the force applied by rope on the Mason, and you cannot take this force applied by Mason within the forces applied on this Mason. This is very important. Furthermore, never include forces that a body exerts on itself, since these cannot affect the body's motion. We have already discussed this one in the previous lecture. Do you have any question here? These are very important information when you are dealing with Newton's laws. So now let me show you 3 examples related to the free body diagrams, and then I will finish this part. Here you see a runner and there is a block, okay, starting block, let's say. So runner applies a force in this direction to the block here, and then this block applies a back force on the runner, okay? Then what about the forces acting on this body? Weight of the body. And then what about normal force? Normal force is this one, okay? This is the normal force. Force applied by block on the runner, okay? Then this normal force has 2 components. One is along the y-axis and the other one is along the x-axis. This component of this normal force applied by the block is equal to the weight. Then along the y-axis, net force acting on this runner is 0, but we have net force acting on the runner along the x-axis. So due to that force, runner accelerates. Any question here? Is it clear for you? Let me show you another free body diagrams. Here we have 2 players with white color on the left side and black color on the right side. So what about the free body diagram for this guy? This player is a freely falling object, and there is only force acting due to the gravity. This is weight of the object. And this guy here on the right side, weight of the guy and normal force applied by the surface, right? So this guy would like to jump. Then in order to jump, this guy should have a net force along the positive y direction. So how to produce a net force along the positive y direction? This guy has to apply a force to the ground, and then the ground will apply a back force in the upward direction. So this guy needs to increase the normal force. If he can increase the normal force, then normal force will be bigger than the weight. Then there will be a net force along the positive y direction. Then this guy can jump. Here there is a swimmer, and then let's try to find forces acting on this guy. We have weight due to the gravity, and there is a buoyancy, kaldırma kuvveti. The water exerts a buoyancy force that counters the swimmer's weight. So this is the weight of the swimmer, this is the buoyancy force applied by the water, and then if they are equal to each other, there is no net force along the y-axis, and this guy would like to move along the left direction, let's say. So in order to move along the left direction, he kicks the water. So this is the F thrust. Kicking causes the water to exert a forward reaction force. This force, this thrust, is a reaction force applied by the water. So this guy kicks the water, and then water applies a reaction force along this direction. So this is F thrust. And then there is a F drag. What is drag? You can consider that the resistance of the water against the movement, okay? So this is the thrust force, this is the drag force. If the thrust force is bigger than the drag force, then this swimmer can have this type of movement. Do you have any question related to the free body diagrams? Okay, with this transparency, I finish chapter 4 and I will continue with chapter 5.